So do the presentation on the current paper. It's titled "To be bridgehead or not to be." It's the question of positioning of an osmium or ruthenium on a metallic bicycle, and they looked at the interaction between the actual aromaticity of the rings itself and the ring strain presented within the ring. So there was a general theory was presented in 1979 by Thorne and Hoffman that there would be 3 classes of the metalloaromatics. These were later confirmed and isolated in the early 1980s and early 2000s. One reoccurring theme that they saw was that the metal would always prefer the non-bridgehead position to the bridgehead position. They thought that that was due to the larger ring strain caused by the rigidity when the metal was positioned in the bridgehead position. So this was just kind of their general basic diagram of how the metal would present itself. They did see in this penciline structure that it would actually like the bridgehead position because it like eliminates the rigidity. It actually pushes this bond inward, and so it decreases the ring strain and actually increases the Gibbs for energy for the ring. But for the hexyl structures, that they did not prefer the bridgehead position. When they looked at the osmium, though, there was a compound, the osmium pentadienyl or pentylene.
Which one was that? The osmium pentylene?
Pentylene. And it was actually confirmed to have the bridgehead position, which they were kind of didn't understand why it would do that. It was examined that the free energy and the computational ring strain actually preferred that position, and so they were kind of understanding which plays a bigger role. Does the aromaticity play out, or does the ring strain play out? Like I said, they also looked at the free energy, and so for these compounds where the metals did not prefer the bridgehead position, the overall energy was actually lower than the bridgehead position. So they were kind of balancing out, was there a greater ability for the ring to be strained yet hold a greater aromaticity for the electrons to still flow around the ring. So then they looked at the actual Gibbs free energy, and as you can see between the bridgehead positions, they're much larger than with the bridgehead position for the penciline. And so they were still trying to figure out that even here.
Sorry, I got a question real quick.
Yeah.
So the 4 structures on the bottom there, were the osmiums in the bridgehead position, or is in the bridgehead in all of them?
So these are where they normally occur.
Yeah.
Because for the hexylene, I guess is what it would be called, was they preferred the non-bridgehead position. Because
So they're just setting that as the reference is 0, and then they're doing that comparison versus the non-favored position.
Where they assume that when you have the penciline, they prefer the bridgehead position. Whereas when you do the benzene rings, they don't prefer the bridgehead position. So when they come here, they just use this as their baseline 0, and anything above that was either a gain in energy, and the movement was a gain in energy, or it was so from here where it preferred to the outside non-bridgehead, it gained energy also. So they were just trying to figure out why these 2 compounds, this compound preferred the bridgehead, even though this one did not, even though they're same general structure. And so they were trying to figure out, was it because of aromaticity, or was it because of the actual ring strain presented within this compound? Because they thought that this would have a larger ring strain since you have less carbon chain. And so they were just trying to figure out, was it the actual Gibbs free, the energy it presented with it was thermodynamically favored, or was it some other compound or a mixture of all 3? And so then they looked at the actual like ring strain. And so one key note that they had was the greater the more less negative difference between like 5 and 6, and then the even to the negative to positive positive of the 7 and 8, which is, go back. So 7 and 8 is corresponding to these two.
Okay. So what is the if you go back to the next one, sorry.
Yeah, I'm gonna have to keep flipping back and forth. But so they said that this should have been like that this would have been preferred, that the non-bridgehead position would have been preferred because it lowered the range, the strain on the bond. But then when they looked back at it from the free energy, it actually increased in energy. So this would have been not favored thermodynamically.
Okay.
And so they were just trying to figure out, because they noted the 7 and 8, the large difference between 7 and 8, and then they noted the difference between 1 and 3, which is these two, the two at the top.
Right, where it's bridgehead or non-bridgehead.
Yeah, and so they even showed that those were much lower, much more positive values than the corresponding non-bridgehead positions. So it was kind of, everything was opposite. Thermodynamically, they shouldn't have been favored, yet based on the ring strain, they should have been favored because you lowered this strain energy. And so they were still kind of confused, like, so they kind of stated that there had to be a relation between the ring strain and the aromaticity, that it had to actually compete with each other, so that, like I said, if the aromaticity dominates over the ring strain, then the more stable isomer will be the aromatic one. And so that's how they kind of figured out that they implemented the free energy for figuring out between the ring strain and aromaticity. And so,
sorry,
yeah.
What does the NICS stand for?
It is a computational method. It stands for it's just they didn't list like what it actually spells out. They just stated that it was a computational method for them, kind of like we use for the Gaussian, and it allowed them to actually go in and set up their structures and then run a calculation for figure out the bond energies. They also used the Gaussian 3 software, and they used nucleus independent chemical shift values.
Fun.
And they also used an anisotropic induced current density, which I will get to in a second, but they call acid, to look at the aromaticity. So then they suggested that the bridgehead positions were more aromatic, but then on the contrary, they figured out that the actual bridgehead would become anti-aromatic, and the non-bridgehead was non-aromatic species. So they were kind of figuring out that there was a play between ring strain and the actual aromaticity, but these compounds were not actually truly aromatic. So then they run the acid, which is their electron density calculation, or the current density calculations, and so they got these kind of weird looking, like cell looking things. And so if they were aromatic species, they exhibited like a clockwise diatropic circulation. So if you see in 4, you see how all the lines kind of current together and they flow in a similar direction. That would induce that they were aromatic. Whereas if you look at 7 and 8, when you get to this middle strain here, the lines become very jumbled. So they are almost anti-aromatic. And then if you look at 1 and 3, the direction of the flow is actually opposite, so there becomes non-aromatic. So they kind of looked at this kind of helped them figure out that there was like a play between the aromaticity and the ring strain. And so then they tried to figure out, like, was this positioning just like independent of the ring strain, or was all three factors playing together? And so finally they kind of concluded that there was also the strain. They did like some strain calculations with the acid, between the acid and the NICS. And so they looked at, like I said, 3 and 4, which is these two, which were the anti, and then 7 and 8, which was the non. And so they looked at that thermodynamically 1 and 2 should have been favored by the thermodynamics calculations they run first, and also that 5 and 6 should have been thermodynamically favored. So they decided to kind of take those out and look just independently on the aromaticity and ring strain, because they would feel that those factors were playing a larger role than just the thermodynamics. And so they looked at the thermodynamics of the 7 and 8, and so they saw that when it was in the bridgehead position, it had a larger output of energy. So when it done this, they did I don't know if this is a splitting, if they removed this.
So they're basically, they're converting the rings, and they're just cleaving them and making them, in this case, just simple methyl groups. So those angles that they show in the middle are the angles that are from the ringed structures, and then they're allowing those structures to relax to what they would be as far as minimizing the strain in the molecule. So they're starting them off in the strained position in that middle structure, and then when it goes to, as they're saying, optimized, I guess in this case, they're making those square planar osmium compounds. It gets a greater reduction than when they're in the non-bridgehead position because there's less initial strain.
Yeah, so, and I guess this is, so the larger the delta E, the more the strain was here. And so they were kind of trying to figure out, so there is a competing factor between strain and aromaticity, because the 7 prefers to be in the bridgehead position, even though it has a larger ring strain, but it allows the compound to be more aromatic.
Gotcha. And
so that's kind of the general gist of, you have to weigh out, if the ring strain becomes too great, so like here, they were also looking at the ring strain should have been lower, but it makes it less aromatic, so the ring prefers the non-bridgehead even though the strain is higher also. So it's kind of looking back and forth to see which would it rather be? Would it rather be aromatic, or would it rather be strained? And so they did a lot of computational methods to kind of figure this out. So for the ring strain, they used the Gaussian 3 stuff, the Gaussian 3 method, and they also looked at the X-ray crystallography of the structure itself, and they did a plot between the NIS and the acid to see the greater differences between that, and so that kind of gave them an idea of which would weigh out in like a certain instances where they basically graphed how much aromaticity a compound got versus its ring strain, and so that kind of looked at, there was a competing factor, and once you reached a certain point you would fall one way or the other. And so in kind of a conclusion, they stated that even though the bridgehead positions were thermodynamically favored, and for the benzene compounds, and the non-bridgehead was favored for the pencil compounds, that ring strain was the kind of one of the deciding factors. And so the ring strain is paired with the isomers, and so when they're comparable to each other, while the differences like in aromaticity is very large, they prefer to be the bridgehead position. And so they kind of decided that each factor played its own kind of key role, but yet they were conductive to each other. So like while you could create all the compounds provided, that they would try to move themselves back to the bridgehead position or non-bridgehead position based on the strain. One thing that they kind of noted on that they would look at later was the possibility of closing the closest bridgehead or non-bridgehead position, and seeing if that kept the compound in the bridgehead or non-bridgehead, depending on what it wanted to do. And so that would be their next step in looking at it.
Cool. Nice work. Clapping, clap, 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 clap. If you go back toward the beginning, it's an interesting study. Keep going. There you go. So for our, let's say, osmapentaline there, how many electrons are we counting on the osmium?
So for the triple bond, is it counting 4 across the triple bond?
If you do a triple bond, if you're doing anionic, there would be a 6 electron donor.
Okay. So 6, 2, 8, 10, 14 surrounding electrons, which osmium is about D6, D8. So that was 16 electrons.